At what values of Ci and Rd a precision clamping can obtain in a peak clamper when the time period of the input waveform is 0.4 seconds. What is the values of Ci and Rd? They are asking us. What has to be the value of Ci and also what is the value of the Rd? So this particular in the circuits of clamper circuit, precision clamping circuits, we have some formulae, and by using the direct formula we can find out what is the value of Ci and Rd. So see now. For precision clamping, Ci and Rd has to be lesser than T by 2. It has to be lesser than T by 2. The time has to be lesser than T by 2, so that 0.1 microfarad into 10 kilo ohms will be almost lesser than 0.4 divided by 2. It gives ultimately, if you do some simplification over here, so your answer is going to be Ci equal to 0.1 microfarad and Rd is going to be 10 kilo ohms. So it's a direct question where you can directly substitute the values and get the answers. So ultimately your answer is Ci equal to 0.1 microfarad and Rd is going to be 10 kilo ohms. Option number A is the correct one. Which circuit converts irregularly shaped waveforms to regularly shaped waveforms? We have studied about different kinds of applications of op-amp, and here some options have been given: Smidge trigger, voltage limiter, comparator, none of the mentioned. Here in this one we have seen in the different classes we have studied about the Smidge trigger. Smidge trigger is a kind of circuit which will be converting an irregular shaped waveforms into a regularized waveforms. So your option A is the correct one. So here you can see the explanation also. What actually Smidge trigger does? Smidge trigger is also called as a squaring circuit because whatever the signal you give it to it, whatever may be the signal kind, it can be a square waveform, it can be your triangular waveform, it can be your pulse waveform, whatever may be the input signal type. Ultimately your output is going to be a square waveform of a Smidge trigger. Smidge trigger will be always producing a square waveform. So because of that reason it is also called as a squaring circuit. It is called as a squaring circuit. So here option A is the correct one. Determine the upper and lower threshold voltage. You are supposed to determine the upper and lower threshold voltage. It's a direct formula which has been given over here. See, one circuit is given to us. We are supposed to find out what is the upper threshold voltage and what is the lower threshold voltage. So in the upper threshold voltage, so see, and now we are having what to say, there is a voltage divider circuit which you can see over here. It's a voltage is getting divided over here at this particular point. So you are supposed to find out what is going to be the voltage. This is upper threshold voltage and here it will be a lower threshold voltage. So now you are supposed to find out the upper threshold voltage over here. So as per the upper threshold voltage, what will be your answer? So ultimately it is a voltage divider circuit. Apply the voltage divider circuit over here and try to find out the upper threshold voltage and lower threshold voltage. So voltage divider circuit means what? In order to find out the voltage at this particular point, it will be, you are trying to find out, I have told in many times in the class that if you are finding out the voltage over here, means you are finding out the voltage across the main resistor which is connected to the input terminal. So this becomes your R1 and this is going to become your R2. So it is R1 upon R1 plus R2 into the voltage. What kind of voltage it is? It is going to be the saturation voltage. What is the saturation voltage? Saturation voltage is nothing else but the 90% of this supply voltage which is supplied here. 15 volts, it is approximately 90%, but actually practically it's a 90% of that one, but theoretically we take it as almost the value of the VCC and VEE. So that's the reason here we have taken it plus 15 and minus 15. So see now formula. VUT is equal to R1 upon R1 plus R2 into V plus VSAT. So what is R1? I have told just now. This is your R1. This particular one will become R1 and ultimately, and this one becomes as your R2. So substitute in the formula. R1 is equal to 10 kilo ohms upon 10 plus 10 kilo ohms plus 250 ohms into plus VSAT. It is ideally we are taking this value, so it's a plus 15 when you do this mathematics, ultimately you are going to get an answer of plus 14.63 volts. In the similar way, substitute this value by minus VSAT, the entire thing is going to be same, only the minus 15 is going to come into this picture. So ultimately you are going to get your answer, it is minus 14.63. So your option number B is a, excuse me, just a minute. Excuse me, just a minute. See here now. There is a printing mistake in this one. Your upper threshold voltage is even it has come as a minus, so it has to be positive. It has to be positive. So kindly make this correction. So your answer is going to be upper threshold voltage is plus 14.63 volts and lower threshold voltage is going to be minus 14.63 volts. So your option number B is the correct one. Option number B is the correct one. Fourth one. What happens if the threshold voltages are made longer than the noise voltages in a Smidge trigger? What is going to happen if the threshold voltages are made longer than the input noise voltages? Then what is going to happen? If this is the case, then the false output transition will be eliminated with the help of positive feedback. The false positive feedback is being used there in order to eliminate the false output transition. So here, whenever this threshold voltages are becoming bigger or greater than the noise voltages, then the false output transitions means what? Which are some transitions, output transitions will be having some false transitions, that glitches will be eliminated. Those kind of false output transitions, we may call it as a glitch. That glitch is going to be eliminated. So option number D is the correct one. Then the fifth one here. You can see down here one particular circuit has been given. You are supposed to find it out, some value of that particular one. Of a circuit, you are supposed to find out what is the output waveform. To a Smidge trigger in a non-inverting configuration, an input triangular wave of 1 voltage is applied. Means 1 volt peak voltage is applied. So it is going to be plus or minus. So now it is 1 voltage is applied. So 1 volt is applied. What will be the output waveform if the upper and lower threshold voltages are 0.25 volts? It means upper threshold voltage is plus 0.25 and lower threshold voltage is minus 0.25. Some options have been given here. Square waveform, pulse waveform, sawtooth waveform, and cannot be determined. So whenever you come across this kind of things, so ultimately irrespective of anything, listen here ma, this is a question which is mainly given to confuse you. It is a question which is mainly given to confuse the students. Why? Because irrespective of anything, we know that whatever may be the signal which is provided to the Smidge trigger, ultimately the output of that particular circuit is going to be in square waveform, because whatever may be the input signal you supply, let it be square waveform, pulse waveform, sawtooth waveform, triangular waveform, whatever may be the input signal, your output is going to be always a square waveform. Your output is going to be always a square waveform. So option A is the correct one. So it's a question which is, the entire question has been asked to you in order to confuse. See, look at the circuit, what kind of circuit is given to you. It's a Smidge circuit. What is the operation of the Smidge trigger? In order to convert whatever may be the input signal, that particular input signal will be ultimately converted into the square waveform. That's the reason, because of that one, Smidge trigger is also called as a squaring circuit. So option A is the correct one here. In which configuration a dead band condition occurs in Smidge trigger? In which configuration a dead band condition occurs in Smidge trigger? Dead band occurs in the Smidge trigger. So let us see the explanation so that you can understand here. Few options are given, like differential op amp with positive feedback, voltage follower with the positive feedback, comparator with the positive feedback, or none of the above. So let us go to the explanation, so you'll get a clarity about how that particular option C is the correct one. So comparator with the positive feedback is said to exhibit some hysteresis. We have seen the hysteresis band in the class. This hysteresis band we have studied in the class. This particular band we have studied in the class. Hysteresis band with the help of positive VSAT and also negative VSAT we have studied. How the particular signal is going to range from one particular point of the voltage to the positive VSAT, and again how it is going to be equal to the negative VSAT. What is hysteresis band? I have told that hysteresis band, you try to remember hysteresis voltage is nothing else but it's almost related to the noise voltage. To what extent a particular circuit can bear the noise. To what extent a particular circuit can bear the noise by providing a correct output. So that thing we are talking about here now. The comparator with the positive feedback is said to exhibit hysteresis, a dead band condition, when input of comparator exceeds the upper threshold voltage. Whenever the input of comparator is exceeding the upper threshold voltage, what happens? Ultimately, the comparison takes place and you are going to get an output with respect to the corresponding input. At this condition, what is happening here? Output is going to switch from positive VSAT to the minus VSAT. That's what we have studied in the previous class. If your output, it is switching like this, if it is switching like this here, whenever, if let me say this is my positive feedback here, positive feedback, and this is positive SAT, sorry, excuse me, not feedback, positive SAT. Whenever it's a positive SAT, if your input signal is crossing this positive SAT, if it is input signal crossing this positive SAT, means what? Ultimately, you're going to have here the switching takes place. If it is positive SAT, so now the switching of your output takes place here. The switching will be happening at the output circuit. So that's the reason here. Whenever the input crosses a upper threshold voltage, the deadband condition will be occurring. At this condition, what happens? The output switch from positive VSAT to minus VSAT. It reverts back to its original state only when again the positive VSAT, the input goes below the lower threshold voltage. So it is related with again upper threshold voltage and also the lower threshold voltage. So I have here I have given you both the thresholds. It's a positive VSAT and again minus VSAT. So whenever the input is going to cross that one particular point, whenever the input is going to cross one particular point, okay, we'll name it as a upper threshold voltage. Excuse me, I'm facing some problem here in order to write that one. I'm facing some problem. Just a minute. It is like this thing we are supposed to kind it as upper threshold VUT, and this is going to be the LUT, lower threshold voltage. So whenever this happens, then only if you can see output, the output is going to switch from high to low and low to high again. It's going to switch from positive saturation to the negative saturation. So option number C is the correct one here. Option C is the correct one. Next one, calculate the hysteresis voltage for a Smidge trigger from the given specification. What are the specifications? Your R2 is equal to 56 kilo ohms. They have given some circuit to us. So as per the circuit, your R2 is equal to 56 kilo ohms. Value of resistor is given to us. And again, you see here, R1 is equal to 100 ohms. R1 is equal to 100 ohms. Then V reference. We have talked about the V reference. This reference voltage, V reference is equal to 0 volts. And again, VSAT of this particular is given as positive and minus 14 volts. Means what? It is going to be almost equal to your plus VCC and minus VW. So let us calculate this one and find out the correct option. So see now, upper threshold voltage formula just now we have seen. Why? Because see, why we are talking about the hysteresis voltage and how this hysteresis voltage is linked with the upper threshold voltage and lower threshold voltage, because we have studied in the concept of this hysteresis voltage. your hysteresis voltage is nothing else but it is a difference of the upper threshold voltage and the lower threshold voltage. Hysteresis voltage is the difference of the upper voltage and the lower threshold voltage. If you know this concept of what is meant by hysteresis voltage, you'll not be thinking about why we are finding out the upper threshold voltage and the lower threshold voltage. So hysteresis, just now we have seen that hysteresis voltage is linked up with the upper threshold voltage and the lower threshold voltage. But what is the relationship between the the relation between the hysteresis voltage and the upper threshold voltage and lower threshold voltage is that the upper threshold voltage minus lower threshold voltage will ultimately give me the formula of hysteresis voltage. So that's the reason why we are going to find out what is upper threshold voltage first and what is the lower threshold voltage from this circuit diagram. Ultimately, again, you are going to find out the voltage at this particular node. This node is going to divide the voltage. It is, we are supposed to apply the voltage division method over here at this particular node, and ultimately with the particular node we are going to take up the calculation. So see now what I told, your this is going to be taken as a R1 is going to taken as a this particular resistance should be taken as R1. Why? Because this is again is linked up with the input voltage or the main supply voltage. So your input signal is almost equal to V reference. So now see now. So upper threshold voltage equal to, apply the voltage division method here. It is R1 upon R1 plus R2 into the plus VSAT. So what is R1 plus R1? R1 is equal to 100 ohms. 100, excuse me. Okay, 100 ohms. Just a minute. I think I have made a mistake over here by typing this this one. You try to look into this one and check the answers. So when you substitute over here, because your it is given as R1 is equal to 100 ohms, and this one, after substituting, you are going to get your upper threshold voltage is equal to plus 25 millivolt and lower threshold voltage is equal to minus 25 millivolt. So ultimately apply in the formula VUT minus VLT, that is 25 minus of 25. So you're going to have 50 millivolts. So 50 millivolts is equal to, this is your answer. This is going to be your final answer. So kindly you just look into this one. I hope I just why, because one of the resistor is having kilo ohms, so I might have been made an error by simply typing this kilo over here. Okay, why? Because we have done this calculations earlier and then I went for the typing part. So that might the reason why I'm very sure about this options answers 25 plus 25 millivolt and 25 millivolt. This might be a typo mistake. So your option C is the correct one, 50 millivolt. Then the next one. What makes the output voltage equal to 0? What makes an output voltage equal to 0 in the practical op-amp? What is going to make an output voltage equal to 0 in the practical op-amp? What is the, if you see the options, it is input offset voltage, output offset voltage, offset minimizing voltage and error voltage. So your option is going to be input offset voltage. Why? Because we know what is meant by input offset voltage. What is an input offset voltage? It is a minimum, even though if you do not supply a minimum input signal, you're going to get some output offset voltage. Means whenever you have not applied some input signal, definitely the output has been obtained at the output of an op-amp. Means definitely there is some kind of noise which is existing at the input terminals, non-inverting and inverting terminal. That noise itself is been amplified at the output. So that noise only we call it as an offset over here. So what makes an output voltage equal to 0? Means if you want to make that output offset voltage equal to 0, you are supposed to apply a minus of that input offset voltage. Whatever is the signal, whatever the offset has been developed at the input terminal, you are supposed to apply a negative value of that input offset voltage, so it becomes 0. It's nothing else but it's simple. Just like when we go for a provisional shop, before weighing any of the provisions which you have purchased, the particular person, shopkeeper, is going to reset that weighing machine. He resets the weighing machine in order to make it as 0. Resetting means what? He is going to subtract the offset which is developed even though the provision has not kept upon the weighing machine. So that thing we are talking here. So in order to make that output 0, you are supposed to apply the input offset voltage, which is exactly opposite to that one. So see now explanation. The input offset voltage is a difference input voltage that exists between the two input terminals of an op-amp without any external input. Even though if you have not applied an external input, there exists some output. Okay, that thing we are talking. So because of that one, we are supposed to force the output voltage to 0. How we are supposed to force the output voltage equal to 0? When you supply some negative value of this input offset voltage over there. When you supply some negative value of the input offset voltage, you are going to get the output equal to 0 practically with respect to the op-amp. That supplying of the negative value of the input offset voltage only we call it as what? Resetting of your weighing machine. That is one of the example. So option A is the correct one. Ninth one. What happens due to mismatch between the two input terminals? If there is a mismatch between the two input terminals in an op-amp, what is going to happen? Let us see the options here. Input offset voltage, it is related with the input offset voltage or it is related with the output offset voltage. Both the, excuse me, again here one typo mistake. Both input and output offset voltage are going to get affected and none of the mentioned here above. What happens due to the mismatch between the two input offset input terminals of an op-amp? The option B is the correct one here. So let us see how it is option B here. So see now the input offset voltage in an op-amp forces the output voltage to become 0 due to the mismatch between the two input terminals. Okay, just now it is related to the previous question. What happens if there is a mismatch between the two input terminals? What happens? Because of that one, you will be developing some offset voltage at the output, and because of that one, we are going to force that negative value of the input offset voltage at the input terminal. So that's how the that's how the output of an op-amp is going to become 0. So what happens whenever the mismatch is there between the input terminals? Output offset voltage is going to exist. So that output offset voltage you are supposed to reduce it to 0. So therefore there will be a voltage produced at the output, and this voltage is called as an output offset voltage. And CMO, you might have studied about one particular term called OOT. Excuse me, where is my pencil? You might have studied about VWOT. VW is what? It's a total output offset voltage. It's a total output offset voltage. If you remove this OOT, if you remove this T, it becomes as a output offset voltage and input offset voltage. It is equal to you have studied VIO and VOO. This is the input offset voltage and the output offset voltages. So option B is the correct one here. Whenever there is a mismatch between the two input terminals, output offset voltage will be existing. Option B is the correct one. Define the polarity of an output offset voltage in practical op-amp. You are supposed to define the polarity of an output offset voltage in an op-amp. See, we have seen in different and many experiments which have been conducted in the laboratory that the output offset voltage can be plus. Even though when we do not apply some input voltage, you might have seen on the multimeter, the output was something like it was something like plus 70 millivolt or minus 70 millivolt. When you have not triggered the input voltage, there was some output was displayed on the screen. So here we can say that the output offset voltage which has been obtained, even though if input is not applied, it can be of both positive and negative polarities. We have even noticed that positive and negative output offset voltages with respect to the circuits. So now option C is the correct one. Option C is the correct one. This here the output offset voltages can be either positive or negative.